10 to the minus 4. Now simplifying this, this can now be written as 1828 divided by 10 to the 5th minus 10 to the 5th times 10 to the minus 4 which is equal to 10. So 10 to the 5th is equal to 100,000 minus 10, that would be equal to 1828 divided by 99,990. So that is equal to the sum of this portion of the number. So now this is equal to taking this portion and writing it as this. Now we need to add 2.7 to that. Okay, how do we do that? So now we get 2.7 plus the fraction of 1828 divided by 99,990, which of course now we have to write that over a common denominator. So this can be written as 2.7 times 99,990 divided by 99,990, which is now the common denominator. We have to, of course, add 1828 to that. Okay, I think at this point I'm going to grab my calculator. So the numerator becomes 2.7 times 99990 equals, add to that, or let me write it out. So plus 1828. So we end up with, this is equal to 271,801 divided by 99,990. Now just to make sure, let's see, this is divisible by 3. I add 2 plus 7 is 9. 8 plus 1 is 9. I have 1 there, so it's not divisible by 3. So probably just want to leave it in this format. This is the fraction form of the number 2.718281828 and so forth. So again, we use the geometric series concept. We separated the 2.7 from the rest of the number. Then we have to recognize what our constant was, and we use the constant 1828 divided by 10 to the 5th, which then left us with our ratio. Our ratio was found by taking two consecutive terms, dividing one by the other, and we got 10 to the minus 4, so this became our common ratio, multiplied by the constant a, and we had it in the form of the geometric series. And the rest of it, oh yeah. Just make sure we did this correctly. Let's divide one by the other to see I get the correct number. So 271,801 divided by 99,990 equals, and I get 2.718281828. That's as far as my calculator goes. So it looks like we did it correctly. So let's just check your answers. And that's how we do it. Welcome to our lecture online. For our second example, to find the moment of inertia, we're going to take a rectangle and I'll place the center mass right on the y-axis there. So how do we find the moment of inertia for something like this? We recognize the symmetry. The left side looks exactly the same as the right side, and if you think of both sides as rotating around the y-axis, you can then realize that we find the moment of inertia of this one side and simply double it. So that means that this now becomes twice the integral, because we're going to have to integrate over all the rule dA's. We're going to integrate the distance to our area element, x squared times dA, but now the limits are going to be 0 over 2. We're only doing it for half the length here, and that's simply doubling the results. So that then becomes equal to 2 times the integral of 0 to L over 2 of x squared, and our area element is the height h times the width dx. Taking the h outside the integral sign, we get 2 times h times the integral from 0 to L over 2 times x squared dx, and that we can easily integrate. That becomes x cubed over 3. This is 2h times x cubed over 3, evaluated from 0 to L over 2. Now, plugging the lower limit, we get 0. Plugging the upper limit, we get the following, which is 2h times, I can take the 3 out here, 2 over 3h, times the quantity L over 2 to the third power, which is equal to 2hl cubed divided by 3 times h. Because 2 cubed is h, so this becomes 1, this becomes 4, or 1/12 hl cubed. Now realizing that the area of that rectangle is length times h, so this can then be, we can take that out, the length is 1/12 hl times L squared. Of course, hl is the area, so it's 1/12 times the area times L squared. And just like we did before, if we assume that this was an object that had mass, the moment of inertia would be 1/12 ml squared. So in this case, instead of using the mass, we use the area, so it's 1/12 AL squared. Now remember what we did in the previous video, when we put the object at the very end, then we realized the moment of inertia is 1/3 AL squared. But in this case, with the center mass at the y-axis, the moment of inertia is 1/12 AL squared. And that's how it's done. Welcome to our lecture online. Now let's see how we test the geometric series. Remember, the general form of the geometric series is the infinite sum from n equals 1 to infinity of some constant a times r raised to the n minus 1. Example, a plus a times r plus a times r squared plus a times r cubed and so forth. You can see the trend. And we know that that is equal to a divided by 1 minus r, where a is a constant and r is the ratio of two consecutive terms. For example, the n plus 1 term divided by the n term, so we have a times r to the n plus 1 divided by a times r to the n. The ratio of that will be r, that's the common ratio. So how do we know if it converges, and what is the sum if it does? We know that the geometric series converges if r is less than 1, or the absolute value of r. So we know that f is going to be, is r less than 1, or let's say the absolute value, question mark. So that's the first thing. Now in our example here, when we look at it, that's not apparent. However, notice that in the numerator here, we have 3 to the first power, 3 to the second, 3 to the third, 3 to the fourth. In the denominator, we have 4 to the first power, 4 to the second. So we're off by an exponent there. If I factor out a 4 out of every term, let's see what happens. So that 4 times, this gives us 1 plus 3 over 4 plus 9 over 16 plus 27 over 64 plus 81 over 256 plus and so forth. So now we realize, okay, I got a bracket there. Now we realize that we have 3 to the first, 4 to the first, 3 to the second, 4 to the second, 3 to the third, 4 to the third, which means we can now rewrite this series as follows. This can now be written as 4 times 1 plus 3 over 4 to the first power plus 3 over 4 to the second power plus 3 over 4 to the third power plus 3 over 4 to the fourth power plus and so forth. And now it's beginning to look like a geometric series. Notice that the first term here typically is the a, and you see that that will be the same for every term. We have a constant 1 times 1 times 1 times 1 and so forth. The ratio is 3/4. Now we can check that by taking, let's say, two consecutive terms. Let's take these two terms right here and see if the ratio does indeed equal 3 over 4. So here let's divide the n plus 1 term, 27 divided by 16. Let's divide it by the previous term, 9 over 4, to see what the ratio is. Of course, when we divide a fraction by a fraction, that is equal to the fraction multiplied by the inverse of the denominator, which is 4 over 9. Let's see here. We have 4 and 16. We can divide both by 4. That gives us 1 over 4. And 9 and 27. 9 goes in 27 3 times. That gives us 1 and 3. So sure enough, that ratio is indeed 3/4. Which means that we verified that this indeed is our ratio. This is the number we factored out. Our constant is a. So we can see that since our ratio, r, is less than 1, therefore we know that the series converges. Next, we want to find the sum. And we know that the sum is going to be equal to a divided by 1 minus r. So therefore the sum is equal to, now that of course would be the sum for this portion. We know that everything must be multiplied times 4, so we get 4 times a over 1 minus r. So this is 4 times 1 divided by 1 minus, the ratio is 3/4. So 1 minus 3/4, that would be 1/4, so this becomes 4 times 1 divided by 1/4. And of course, divided by 1/4 same as multiplying times 4. This is 4 times 4, which is 16. So this determines that the series does indeed converge, and that the sum is equal to 16. And that's how it's done. Welcome to our lecture online. In this particular infinite series, we have what we call the P-series. We have a couple of examples. The P-series, the general equation of that would be the infinite sum from n equals 1 to infinity of 1 over n to the p power. Now in this example, t is equal to 3, so we have 1 over n to the third power. In this example, we have 1 over the square root of n, so in this case, t is equal to 1/2. The test tells us that if t is greater than 1, we know that the series will converge. So that satisfies that condition, and therefore the first example does converge. But the second example, here we can see that t is less than 1, and therefore we can conclude that the series diverges. It seems kind of odd in a way when you use your intuition. Sometimes your intuition will get you into trouble, but even though the denominator continues to grow, because the square root of a growing number will still grow, but it doesn't grow fast enough, and therefore the series does not converge. So we need to know for sure, is to check to see the value for p is greater than 1, it converges.